The Dark Side of the Moon, Secrets Hiding Beyond the Craters. Part 1. The Mystery of the Lunar Far Side. For eons, humanity gazed upon the familiar face of the moon, its craters and maria etched into our collective consciousness. Yet, a veil of mystery shrouded its opposite hemisphere, forever hidden from terrestrial view. This dark side, more accurately termed the far side, remained an enigma, a canvas for speculation and scientific curiosity. Its existence fueled imaginations and spurred the early space race, offering a tantalizing glimpse into a lunar landscape untouched by direct human observation. The sheer inaccessibility made it a prime target for exploration, promising revelations about the moon's formation and evolution that the near side could not provide. The challenge of reaching and imaging the far side was immense, pushing the boundaries of early rocketry and orbital mechanics. When the Soviet Union's Luna 3 probe finally delivered the first grainy images in 1959, a new world began to unfold. These initial snapshots, though crude, confirmed a dramatically different topography, sparking a renewed scientific interest. The lack of the vast, dark maria that characterized the near side was immediately apparent, hinting at underlying geological processes distinct from what astronomers had studied for centuries. This discovery initiated a long journey of understanding the true nature of Earth's closest celestial neighbor. The term dark side is a misnomer, as both hemispheres of the moon experience equal amounts of sunlight over the course of a lunar month. It's the far side because it perpetually faces away from Earth due to a phenomenon called synchronous rotation. This constant hiding fostered a sense of the unknown, allowing for myths and fantastical stories to take root in popular culture. Scientists, however, sought concrete data, eager to peel back the layers of this celestial secret. The far side represented a pristine laboratory, potentially holding clues to the early solar system, undisturbed by terrestrial interference. Understanding the far side's composition and structure became a priority for lunar science. Early theories posited a uniform lunar crust, but the initial images from Luna 3 suggested otherwise. The heavily cratered terrain, seemingly more ancient than the near side's smoother plains, hinted at a different history. This stark contrast raised fundamental questions about the forces that shaped the moon and why such a dramatic hemispheric dichotomy exists. The scientific community recognized that unlocking the far side's secrets was crucial to piecing together the moon's complete geological narrative. The drive to explore the far side was not just scientific, it was also a testament to human ingenuity and our insatiable desire to push boundaries. Each mission that gathered data from this hidden hemisphere contributed to a growing mosaic of understanding. From orbiters mapping its surface with increasing resolution to future landers exploring its regolith, the far side continues to beckon. Its enduring mystery, once a barrier, has become a powerful motivator for technological advancement and scientific discovery, promising even more profound insights in the years to come. Part 2. Why one side always faces Earth. The phenomenon of why one side of the moon always faces Earth is known as tidal locking, a captivating dance choreographed by gravitational forces. This celestial waltz is not unique to the Earth-Moon system, but is common throughout the cosmos, affecting many moons and even some exoplanets orbiting their host stars. It is a stable configuration, where the moon's rotation period precisely matches its orbital period around Earth. This precise synchronization ensures that from our terrestrial perspective, we always observe the same lunar face, year after year, century after century. The genesis of tidal locking lies in the slight gravitational bulge created on the Moon by Earth's pull. Earth's gravity exerts a differential force across the Moon's body, slightly elongating it. This bulge, though subtle, is key. As the Moon initially rotated faster than it does today, Earth's gravity acted upon this bulge, constantly tugging it back into alignment. This gravitational braking mechanism gradually slowed the Moon's rotation over billions of years, until its rotation period matched its orbital period, locking it into its current state. Imagine the Moon as a slightly lopsided object. Earth's gravity would naturally pull harder on the closer, more massive side, creating a torque. This torque would continually work to align the Moon's longest axis with Earth. Over vast stretches of cosmic time, this persistent gravitational influence acted like a brake, draining rotational energy from the Moon. Eventually, a stable equilibrium was reached where the Moon's rotation perfectly matched its revolution, minimizing the energy required to maintain its orientation relative to Earth. The process of tidal locking is not instantaneous. It's a gradual evolution spanning eons. Early in its history, the Moon likely spun much faster, with both sides visible from Earth over time. However, the relentless gravitational interaction with Earth steadily diminished its rotational energy. This energy was dissipated primarily as heat within the Moon's interior, a testament to the immense power of tidal forces. This ancient process ultimately sculpted the familiar lunar face we observe today, making the far side a truly hidden realm. The stability of tidal locking is remarkable, ensuring that the far side remains largely out of direct sight from Earth-based observers. While libration, a slight wobbling of the Moon, allows us to peek around the edges and glimpse a small percentage more than 50% of its surface over time, the vast majority of the far side remains perpetually averted. This fundamental astronomical principle underpins much of the scientific interest in the far side, as its shielded nature may have preserved unique geological and environmental conditions for billions of years. Part 3: Differences in Crust and Geology. One of the most striking revelations about the lunar far side is its profound geological difference from the near side. While the Earth-facing hemisphere is characterized by extensive, dark volcanic plains known as maria, the far side is dominated by heavily cratered highlands. This hemispheric dichotomy is so pronounced that it immediately became a central puzzle for lunar scientists. The absence of vast maria on the far side suggests fundamentally different geological processes at play during the Moon's early history, challenging initial assumptions about a uniform lunar structure. The lunar crust itself is significantly thicker on the far side compared to the near side. Data from gravity mapping missions has confirmed this asymmetry, with the far side crust being roughly 10 to 15 kilometers thicker on average. This difference in crustal thickness is a crucial piece of the puzzle. A thicker crust would have made it more difficult for molten basaltic lava, which form the maria, to reach the surface and erupt. This physical barrier largely explains why the far side lacks the expansive dark plains that are so prominent on the near side. The prevailing scientific theory for this crustal asymmetry involves the Moon's formation and early evolution. One leading hypothesis suggests that the Moon formed from debris ejected after a massive impact between a Mars-sized object and early Earth. In this scenario, two bodies of molten rock, one larger and one smaller, may have coalesced. The smaller body could have been captured by the larger, impacting it slowly and splashing material, primarily to one side, leading to a thicker crust on that hemisphere. Another compelling hypothesis relates to Earth's early thermal influence. Immediately after the Moon's formation, Earth was still incredibly hot. The side of the Moon facing Earth would have been subjected to greater radiant heat, keeping its mantle warmer and allowing for more widespread volcanism to form the Maria. The far side, shielded from this intense heat, would have cooled faster, developing a thicker, more rigid crust that inhibited the ascent of magma, thereby preserving its ancient cratered highlands. The geological distinctiveness of the far side offers an invaluable window into the Moon's formative years. Its heavily cratered highlands are believed to be some of the oldest surfaces on the Moon, potentially preserving records of the intense bombardment period in the early solar system. Studying these ancient terrains provides crucial data for understanding impact dynamics and the early distribution of matter in our cosmic neighborhood. The far side, therefore, serves as a natural time capsule, holding secrets that the more volcanically resurfaced near side cannot. Part 4. The South Pole Aitken Basin. Among the many striking features on the lunar far side, the South Pole Aitken Basin stands as an unparalleled geological marvel. It is the largest and deepest confirmed impact basin, not only on the Moon but in the entire solar system. A colossal scar stretching approximately 500 kilometers in diameter and plunging up to 13 kilometers deep. This immense structure is a testament to an unimaginably powerful impact event that occurred billions of years ago, profoundly shaping the Moon's crust and interior. The sheer scale of the South Pole Aitken Basin makes it a prime target for scientific investigation. Its vast size means that the impactor must have penetrated deeply into the Moon's crust, potentially excavating material from the lunar mantle. This exposed mantle material, if present on the surface, would offer a unique opportunity to study the Moon's internal composition directly, without the need for deep drilling. Understanding the composition of the basin floor is crucial for refining models of lunar differentiation and the Moon's internal structure. Scientists believe the impact that formed the basin occurred very early in the Moon's history, during the intense period of bombardment known as the Late Heavy Bombardment. This era was characterized by a deluge of asteroids and comets impacting the inner solar system bodies. The South Pole Aitken Basin likely represents one of the largest and last of these gargantuan impacts, its existence profoundly influencing subsequent lunar evolution and geology, particularly on the far side. The basin's location, straddling the lunar South Pole, presents both scientific opportunities and logistical challenges for exploration. The polar regions of the Moon are of particular interest due to the potential presence of water ice in permanently shadowed craters. The combination of the deep basin and the polar environment makes the South Pole Aitken Basin a compelling site for future missions aiming to study both ancient lunar geology and accessible resources. Its unique setting could yield insights into both deep lunar history and practical applications for future human exploration. Studying the South Pole Aitken Basin provides critical insights into impact mechanics on a planetary scale. The immense energy released by such an impact would have caused widespread melting, faulting, and seismic activity across the Moon. The basin's geology can help scientists calibrate impact models, offering a better understanding of how large celestial bodies respond to colossal collisions. It remains an active area of research, with ongoing missions and future proposals aiming to unravel its many remaining secrets and unlock its full scientific potential. Part 5. China's missions to the far side. China has emerged as a leading pioneer in lunar exploration, particularly with its ambitious and successful missions to the Moon's far side. The Chang'e program, named after the Chinese goddess of the Moon, has systematically pushed the boundaries of what is possible in lunar science and exploration. These missions represent a significant technological achievement, demonstrating China's growing capabilities in deep space navigation, landing, and robotic operations, especially in an inherently challenging environment. The landmark achievement came with the Chang'e 4 mission, which made history in January 2019 by successfully performing the first-ever soft landing on the lunar far side. This feat required overcoming immense technical hurdles, primarily the lack of a direct communication link with Earth. To solve this, China launched a relay satellite, Kekaro, positioned in a halo orbit around the Earth-Moon L2 Lagrangian point, enabling communications between the far-side lander and ground control. This innovative solution was crucial for mission success. The Chang'e 4 lander deployed the Yutu-2 rover, which has been methodically exploring its landing site within the von Karman crater inside the larger South Pole Aitken Basin. The rover is equipped with a suite of scientific instruments, including a panoramic camera, a visible and near-infrared spectrometer, and a ground-penetrating radar. These instruments are designed to characterize the lunar regolith, identify mineral compositions, and probe the subsurface structure, providing unprecedented data from this previously unexplored region. Data from Yutu-2 has already yielded significant scientific findings. The rover's ground-penetrating radar has provided the first subsurface images of the far side, revealing layers of ejecta from impact events and helping scientists understand the geological history of the region. The spectrometer has analyzed surface materials, offering clues about the composition of the lunar mantle and the processes that shape the South Pole Aitken Basin. These insights are invaluable for refining models of lunar formation and evolution. China's ongoing commitment to lunar far-side exploration underscores its strategic vision for space. Future missions are planned to return samples from the far side, which would be a monumental scientific achievement. Such samples, particularly from the South Pole Aitken Basin, could provide definitive evidence of mantle material and further constrain the Moon's early history. China's pioneering efforts are not only advancing lunar science, but also paving the way for international collaboration and future human presence on the far side of the Moon. Part 6. The Dream of Radio Telescopes on the Moon. The lunar far side presents an unparalleled environment for radio astronomy, an environment that is virtually impossible to replicate on Earth. The dream of establishing radio telescopes on this shielded hemisphere stems from its unique characteristic as a naturally quiet zone, free from the incessant radio frequency interference, or RFI, generated by human activities on Earth. This RFI, from television broadcasts and cell phones to Wi-Fi signals and satellites, creates a deafening cacophony that increasingly hampers terrestrial radio observatories. Placing a radio telescope on the far side would offer an unobstructed view of the universe in low-frequency radio waves, a spectral window that is currently almost completely opaque from Earth. These long wavelengths are crucial for observing some of the earliest phenomena in the cosmos, such as the Dark Ages before the first stars ignited, and the epoch of reionization when the first stars and galaxies began to illuminate the universe. Detecting these faint, ancient signals requires an utterly pristine radio environment. The Moon itself acts as a massive shield, blocking out Earth's radio noise. This natural barrier makes the far side an ideal location for detecting extremely weak extraterrestrial radio signals that would be completely overwhelmed by terrestrial interference. Such a facility could potentially revolutionize our understanding of cosmology, providing direct observational evidence of the universe's formative moments and the emergence of the first structures. It is a scientific frontier with immense discovery potential. Beyond cosmology, a Farside radio observatory could also play a critical role in the search for extraterrestrial intelligence, SETI. By operating in a quiet radio environment, researchers could listen for artificial signals without the constant background noise of human civilization. The ability to distinguish genuine alien transmissions from terrestrial chatter would be vastly improved, opening up new avenues for exploring the possibility of life beyond Earth. It offers a unique sanctuary for listening to the cosmic symphony. Developing and deploying such an observatory would be a formidable engineering challenge, requiring advanced robotics, autonomous operations, and robust power systems. However, the scientific payoff would be immense, justifying the significant investment. Missions like China's Chang'e 4 have already demonstrated the feasibility of operating on the far side, bringing the dream of a lunar radio observatory closer to reality. It represents humanity's next great leap in observing the universe, leveraging the moon's natural advantages for groundbreaking astronomical research. Part 7. Lunar resources like helium-3. Beyond its scientific allure, the moon holds significant promise as a source of valuable resources, with helium-3 being perhaps the most tantalizing. This rare isotope of helium is not common on Earth, but is relatively abundant in the lunar regolith, deposited over billions of years by the solar wind. Helium-3 has garnered considerable attention because of its potential as an ideal fuel for nuclear fusion reactors, offering a clean and efficient energy source with minimal radioactive byproducts, a holy grail for future energy production. Unlike the deuterium-tritium fusion reactions currently being researched, helium-3 fusion is aneutronic, meaning it produces charged particles rather than neutrons. This significantly simplifies reactor design and reduces issues associated with neutron activation of reactor components, leading to less radioactive waste. The prospect of harnessing this virtually limitless clean energy source from the moon has fueled visions of future lunar mining operations and energy independence for humanity, transforming our energy landscape. Estimates suggest that the lunar surface could contain millions of tons of helium-3, vastly exceeding Earth's limited reserves. While the concentration in the regolith is low, the sheer volume of lunar soil means that substantial quantities could be extracted. The process would involve heating the regolith to release entrapped gases, which would then be separated to isolate the helium-3. This requires significant infrastructure and energy on the moon, but the long-term benefits could be transformative. The economic feasibility of lunar helium-3 mining remains a subject of intense research and debate. The initial investment in mining equipment, processing plants, and transportation systems would be enormous. However, if terrestrial fusion power becomes a reality and a robust market for helium-3 emerges, the incentive for lunar resource extraction would be compelling. It could create an entirely new space economy, driving technological innovation and opening up new frontiers for commercial enterprise beyond Earth. Beyond helium-3, the moon also contains other potentially valuable resources such as oxygen, silicon, iron, and aluminum, embedded within its rocks and regolith. These can be used for in-situ resource utilization, or ISRU, to support lunar colonies, reducing the cost and complexity of bringing materials from Earth. While helium-3 is the star attraction for energy, the broader range of lunar resources underscores the moon's potential as a critical stepping stone for expanding human civilization into the solar system, providing the raw materials for sustained presence. Part 8. Myths and Music About the Dark Side. The hidden nature of the lunar far side has long captivated the human imagination, birthing a rich tapestry of myths, legends, and artistic interpretations. Before its true nature was revealed by spacecraft, The dark side was a blank slate for fantasy, a place where anything could reside, free from human scrutiny. This inherent mystery imbued it with an almost mythical quality, allowing it to become a powerful symbol in literature, folklore, and especially music. One of the most enduring cultural artifacts inspired by the far side is Pink Floyd's seminal 1973 album, The Dark Side of the Moon. While the album's themes delve into human experiences like madness, conflict, and the passage of time, its title cleverly taps into the public's fascination with the unknown lunar hemisphere. The album became a cultural touchstone, forever linking the concept of the hidden and unexplored aspects of the human psyche with the enigmatic far side of our celestial neighbor, creating an evocative metaphor. Beyond the iconic album, the far side has frequently appeared in science fiction as a clandestine location for secret bases, alien civilizations, or hidden ancient artifacts. Its perpetual concealment from Earth provides a perfect narrative device for authors to explain how advanced beings or technologies could operate unnoticed. This trope highlights humanity's deep-seated curiosity about what lies beyond our immediate perception and our tendency to populate the unknown with extraordinary possibilities. Ancient cultures, long before telescopes and spaceflight, often wove stories around the moon's phases and its unchanging face. While they couldn't conceive of a far side in the modern sense, the moon's consistent presentation of one face might have contributed to its mystical aura. It was seen as a constant, a sentinel in the night sky, its hidden half perhaps representing the unseen forces that influenced human destiny or the mysteries of the divine. The allure of the far side continues to inspire contemporary artists and writers, even with our increased scientific understanding. Its designation as a radio quiet zone, for instance, has fueled new narratives about extraterrestrial communication or clandestine astronomical observations. The blend of scientific fact and enduring mystery ensures that the moon's far side will remain a fertile ground for creative expression, continuing to spark wonder and inspire new stories for generations to come. Part 9. The Moon as a Stepping Stone to Mars. The moon, and particularly its far side, is increasingly viewed not just as a destination in itself, but as a crucial stepping stone for humanity's ultimate journey to Mars and beyond. Establishing a sustainable human presence on the moon would provide invaluable experience, test vital technologies, and develop operational protocols necessary for future, more distant deep space missions. It serves as a proving ground, minimizing risks and maximizing the chances of success for expeditions to the Red Planet. A lunar outpost, potentially on the far side due to its unique advantages, could act as a logistics hub and a staging area for Mars missions. Resources extracted from the moon, such as water ice for rocket fuel and life support, could significantly reduce the mass that needs to be launched from Earth, dramatically lowering costs. This concept, known as fueling depots, transforms the moon from a resource consumer into a resource provider, making interplanetary travel more feasible and sustainable. The extended duration of lunar missions, lasting months or even years, would allow astronauts to gain invaluable experience living and working in a reduced gravity environment. This experience is critical for understanding the long-term effects of space on the human body and developing countermeasures for the challenges of living away from Earth. A lunar habitat could also serve as a testbed for closed-loop life support systems, radiation shielding, and remote medical care, all essential for long-duration voyages to Mars. The unique environment of the far side offers specific advantages for a Mars staging base. Its radio quietness could be beneficial for communications relay to and from Mars without terrestrial interference, and its stable regolith could provide excellent shielding for habitats against solar radiation and micrometeorites. A lunar base also offers a relatively accessible abort-to-Earth option, enhancing safety margins for crews compared to a direct mission to Mars, which offers no such immediate escape route. Ultimately, the Moon's role as a stepping stone is about building capabilities and confidence. By mastering the challenges of sustained lunar presence, we build the technological and operational maturity required for the vastly more complex and demanding journey to Mars. Every lesson learned on the Moon, from resource utilization to crew psychology, directly contributes to our readiness for sending humans to our neighboring planet and establishing humanity as an interplanetary species. Part 10. Future Colonies on the Lunar Far Side. The vision of future colonies on the lunar far side, once purely the realm of science fiction, is slowly but surely transitioning into a tangible goal for space agencies and private companies. The unique attributes of this hidden hemisphere, combined with advancements in technology, are making the prospect of permanent human settlements there increasingly attractive. Such colonies would represent a monumental leap for humanity, expanding our civilization beyond Earth and establishing a foothold in the cosmos. One of the primary drivers for far-side colonization is its scientific potential. A permanent human presence would enable unparalleled opportunities for deep space astronomy, utilizing the radio-quiet environment for massive observatories. Astronaut geologists could conduct extensive field research in areas like the South Pole Aitken Basin, providing real-time analysis and sample collection far beyond the capabilities of robotic missions. The far side would become a premier research outpost, unraveling cosmic mysteries. The potential for resource utilization, particularly water ice in permanently shadowed regions, is another key factor. These resources could be used for life support, breathable air, and the production of rocket propellant, making a far-side colony more self-sufficient. A base capable of producing its own fuel could become a refueling station for missions to Mars and beyond, transforming the economics of space exploration and enabling more ambitious ventures into the solar system. Establishing a colony on the far side presents significant engineering and logistical challenges. Building shielded habitats to protect against radiation and micrometeorites, developing robust life support systems, and ensuring reliable power generation are paramount. Communication with Earth would still rely on relay satellites, but advanced autonomous systems and 3D printing technologies could help in constructing infrastructure using local materials, reducing reliance on expensive imports from Earth. Beyond scientific and economic benefits, lunar far-side colonies represent a critical step for humanity's long-term survival and expansion. They offer a tangible Plan B should Earth face catastrophic events and foster the development of a spacefaring culture. The dream of a permanent human presence on the Moon's far side is not just about survival or science. It is about extending the human spirit of exploration, innovation, and ultimately ensuring the enduring future of our species among the stars.